This is AIS's portable multi-frequency microwave system. The major components are we have a laptop, runs the software and communicates to the encoder and to the VNA. I'll explain in a moment. This is a control block that communicates to the encoder. This is the device that allows us to start and stop the antenna movement. This is a fixture in the back here that contains a tray that basically holds our microwave system at reasonably precise locations across the part. We rotate the part and this little fixture to scan it. This is a vector network analyzer, which is kind of the heart of the system. We'll get to it right now with the calibration tool. We do 3 points of calibration, then we remove this device, and we mount the antenna on the vector network analyzer in the tray, and then we're able to mount it so that it's positioned correctly, and then we'll rotate the pipe as we collect data. I have the laptop open now. I'm going to start the software associated with the calibration of the VNA. We'll let that load. And then the process of calibration, I select calibration. I select the device that I'm using. In this case, it is, excuse me, too far. This device is the one that I'm using. And then basically what I do is I go through each one of these calibrations by rotating the points that's connected to the device, the VNA. And I'll go through and check each one of those, and each time I do that, then I'll check the box here associated with each one of those calibrations. And once I do that, then I can apply that calibration. All right. Well, what I'm going to do in this case, because I've done this, I'm going to go, let me go to File. I'm going to recall a calibration. I'm going to select the one for today, August 1st, 2023. And I'm going to open that file, and I'm going to select OK. At this point, that software is ready to use as part of the data collection system. Now that we've calibrated the VNA, we need to open up the data acquisition software. We'll start the program. The first thing it does is it brings back up the calibration screen for the VNA. We've already completed that process, so we'll recall that file. And then we'll go back in the background to the data acquisition software and hit Hide VNA. We'll do Finish Setup. We'll hit Apply. We'll hit Next. The fact that we have an IP address here tells us that we are communicating with the VNA, so all should be good. We hit OK. We only need to make a few adjustments on this screen. The phase current needs to be 1.5 amp. The X dimension is the dimension of movement along the axis of the pipe. In this case, it'll be 180 millimeters. X resolution is the individual increments we move the device. That will be 4 millimeters. The Y dimension is essentially the circumference of the part. We'll make that 360 millimeters, and the Y resolution should be about 10 millimeters, should be sufficient. Once that is done, we're ready to move over and reset 0 with our encoder and start collecting data. Now that we've got the software set up, we've selected a joint to put in the fixture to scan. This happens to be number 3. We do want to point out the posts are still present on the coupler. We will leave those on the coupler, and when we scan, we'll scan before it, basically right here, and we'll scan around this way, and we'll stop just before we get to the coupler the other way as we come around. Okay. Now what we need to do is take the antenna and place it on the left-hand side as our start point, and then essentially we'll scan across, we'll rotate the pipe, and we'll scan back across and continue the process until we finish scanning the pipe. So let me rotate this pipe to the start position, and we'll move the encoder and antenna back to 0. And we usually do this as a 2-step process where we move it to generally the end of the coupler, and then I want a little extra room for scanning so that we can clearly see the end of the pipe. And basically now that becomes our 0 point, and we'll hit the start and begin collecting data on this coupler. And that's stepping at 4 millimeter increments across the coupler. and over into the pipe, so we know clearly where the coupler ends in this configuration. Now that it's finished that pass, I'll index the pipe around and move the scanner back across the couple. I'll repeat this process until I've gone all the way around the couple. The antenna has now moved to the end of that particular stroke. What I'll do at this point in the lab setup is rotate this the appropriate amount. Then I'll restart the scanner, heading back to the left. With each movement of the scanner, each line, you get a line of data in the data acquisition software. In the data acquisition software, you can see shades of blue captured between shades of green. The blue is the actual EF wires themselves, and the green on the end is beyond the coupler itself, which you'll clearly see in the data. I'll index it again. We'll move the scanner back to the right again. We'll select the next line of data. This process continues till we've gone all the way around the coupler. We're wrapping up the scan now as we approach the post from the other side. We've got one or two more scans to make here, and then we'll stop just short of the post. Again, the zone in between the posts will not be scanned. Once that is done, we'll save this data collection file as an analysis file, and we'll use the analysis software to do the analysis. This is the last line of data taken on this particular component. After this completes the scan, we will save the scan. We do that by selecting save it as an SDT file, which you've done here. Then we select the folder or file we want to put it in, give it a name. I'll just call it 3. And we'll hit save. And that completes the data collection on this part. This is the analysis software we've opened. We've also loaded the file that we just collected on joint number 3, as you can see here in the top. Basically, you've got several different parameters we can include, and won't go into the details about those at the moment. But basically, you've got a dead zone here in the horizontal B-scan of the antenna, the space it is off of the part itself. And here you can clearly see the electrofusion joint. These two areas, you can see the separation here. And that is also shown over here in the IFFT window, where you can see a large area of non-fusion. You can see inconsistencies in the thickness of the fusion joint, both top and bottom. You can also notice that there's some gap issues that might be a little beyond what would be normal. The best way to analyze the data is to compare it to other joints, finding a good known joint, and then look at the differences between the two. But clearly here we have some issues with fusion in the area of concern. This is the second EF joint you provided, EF joint number 9. We're looking at the data from number 9. The left-hand side parameters are very similar as we want to compare equally between the different joints. Again, same thing with the B-scan over here. You can see the area of fusion. And if you go over here to the IFFT view, you can clearly see we've got some issues as the scan began, some variations in width of the fusion, and it appears that we might have some spacing problems between the ends of the pipe before the fusion was made.
This photo shows our microwave antenna attached to our chain scanner. This scanner allows us to rotate the antenna 360 degrees around the OD of the part being examined, while maintaining the proper air gap needed for the antenna. The scanner allows us to inspect parts with an OD from 4 inches to 30 inches.